ওইখানটা দাঁড়িয়ে
So a very good morning to all the participants from various colleges present over here. A very good morning to our Dhruvashi sir, Department Chair, CSC, IT and EC Studies, and a very good morning to Professor Dr. R.K. Patro sir, Dean of Management Studies. A very good morning to all my colleagues and the volunteers present here. Now, I welcome Dr. Amit Kumar Vashi from EC Department welcome you all to the 4th day of 6-day FDP on bridging academia and industry and NEP-Centric Approach to AI, Robotics and Industry 4.0 and 5.0. Now, let us all join together to give a very hearty welcome to our distinguished speaker, the Honorable Mr. Saugato Bhattacharjee, who will grace today's session by sharing his expertise on the topic preparing students for Industry 4.0 and 5.0 careers. A very good morning to you, sir. We are really honored to have you amongst us today. A very big round of applause for our distinguished speaker. Now I request Dr. Dhruvashi sir, the Department Chair, CSC, IT and EC Studies, to felicitate our speaker with Uttoriyo badge and a memento. Now our Dhruvashi sir will be joined by Dr. R.K. Patro sir in felicitating our today's speaker. So I request both Dhruvashi sir and R.K. Patro sir to please come to the dais and felicitate sir. So here we have Dr. R.K. Patro sir felicitating the speaker with Uttoriyo. A very big round of applause. Then we have Patro sir again felicitating the speaker with the badge. And we have to Thank you, sir. Thank you, Patro sir. Thank you, Dhruvashi sir, for felicitating our speaker. Now we have, so kindly take the seat. Now we have a brief profile of today's eminent and distinguished speaker. Mr. Saugato Bhattacharjee is a senior staff engineer manager for Samsung Semiconductor India Research and is based in Bangalore, where he specializes in the field of VLSI related to integrated circuit and chip design and verification. His expertise spans multiple domains in VLSI like RTL design and ASIC verification, and he also has profound knowledge in the field of blockchain. He has 10 plus years of experience in the semiconductor domain and has previously worked in organizations like Intel. He published and presented several papers in prestigious international conferences like TED, UVCON, CDN, LIVE, and VLSI related topics. He also drives innovation within his company and has helped people with their queries and introduced novel methods for increasing productivity within the projects. He holds an MTech degree in microelectronics from BITS Pilani and also has a PG diploma from CTAC in VLSI. He is currently pursuing his second MTech from IIT Patna in Big Data and Blockchain. He is a TEDx speaker at UT, where he spoke about different innovation strategies and how to develop lateral thinking. The talk is yet to be published. Besides this, he is also awarded the LinkedIn Top Voice Award for writing content on LinkedIn and helping millions of people across different geographical locations. He believes that knowledge related to technology and science should reach the maximum number of people possible so that it brings a unique impact to society for the benefit of mankind and is always ready to provide his helping hand to the person in need. Keeping this in mind, he started writing in Quora in 2017 and was awarded Top Writer of Quora in 2018 due to his contribution to the engineering community and helping many people with their queries. Later, intending to help as many people as possible, he started writing on LinkedIn and is recognized by LinkedIn multiple times for his contribution. He currently has over 40,000 followers on LinkedIn and is actively helping the VLSI community with their queries and also monitoring them when needed. He is also a keynote speaker at several engineering colleges and often visits there to interact with the students and share his knowledge with them. He is also actively involved with an NGO called CRY. He is volunteering for multiple activities like translating content from English to regional languages and social media campaigns during the COVID outbreak, and now is actively participating in offline activities like teaching. I very much welcome you, sir, and I would like to invite you to begin our session. Thank you, sir.
Before we put the microphone to Mr. Shobhata Bhattacharya, it's a message from our end. Like, while I consider my experience to dealing with students, as I got the opportunity to work some of the best brands in our country, I've seen that the main difference between a student of so-called big institutions in our country, I'm not talking about the IITs or NITs, but even those what are the private institutions we have in our country, which is known as big. And the students from our colleges, the big difference, whatever I have seen, is that they're getting exposure. If a student in our colleges gets same kind of exposure that the student in those big institutions they get, I don't think that our students will be 1 inch behind them. So while I was talking to Shobhato, I know him since long, and I have seen his career profile. So while I was talking to him, I have learned a lot from him that how can a student get good exposure to make him or her employable for a big organization like Intel, where he has also worked. So considering his vast experience, he is also born and brought up from a state which is not so-called developed, but then because of his exposure, he got the opportunity to work some of the world famous brands considering Intel and Samsung Semiconductor. So if you go through the recent messages from AICTE and UGC in last 2-3 days, day before yesterday, the UGC chairman told that internship is mandatory for all courses, specifically for technical courses. And yesterday only the chairman of AICTE has mentioned that yes, AI will take many jobs. That is an issue that we are discussing for the last few days. But then generative AI will create lot many opportunities for us. So we want our students to reskill, to upskill themselves, and it's a part of lifelong learning. Now, our student will be motivated for lifelong learning. In being a professor, we are doing so. So, considering that, I have requested to highlight, particularly as he is specialist in ASIC and VLSI, and currently working in blockchain and machine learning in hardware level. So, we found that he is the ideal person to tell us, to guide us how to prepare ourselves so that we can make our students ready for industry 4.0 and 5.0. So our sincere thanks and gratitude to Mr. Shobhat Bhattacharya, although this is his second visit to our campus. I'm sure that his session will be very beneficial for all of us. Thank you.
Good morning, everyone. So, so as we all know, the title of today's presentation is Preparing Students for Industry 4.0 and 5.0 Careers. So this whole presentation is divided into 4 major subsections. In the first section, I am going to discuss about the different technologies and trends that are going to drive the Industry 4.0 or already driving today's current industry, different industry standards. In this section, I am also going to discuss about the upcoming trends and how the evolution from Industry 1.0 to 4.0 took place, and how the teachers can actually mentor their students to learn different technologies and how they keep themselves motivated for pursuing more and more different technologies to successful in their careers. In the second section, I am going to discuss about the VLSI and the semiconductor industry in depth, where I am going to discuss about different career opportunities in VLSI and semiconductor, what are the different skills needed to learn them, how to acquire those skills. And since my background is from ASIC verification, I go into ASIC verification in big depth so that it will kind of internet how the semiconductor industry evolved over the last several few decades. In the third section, I am going to discuss about one more technology which is driving the industry 5.0, that is the blockchain. And similarly, like the previous section in VLSI, I am going to discuss about the overall blockchain technology in detail, and what are the different skills needed to learn blockchain, what are the different career opportunities involved. And in the last section, I will touch upon artificial intelligence not in depth but a brief overview, because the term is very much common to us, and after the generative AI like ChatGPT comes into picture, we are much more aware of those kind of technologies. In both the cases, like blockchain and AI, I will also show how we can kind of interlink into different other technologies. In my case, how I am interlinking both blockchain and AI to leverage the problems which exist in the semiconductor industry and how we can solve them through putting much more innovative ideas into practice. So, before starting the presentation, I would like to quickly introduce about my VLSI journey, my semiconductor journey in overall. So my journey starts right after my engineering, which I completed in electronics and telecommunications. So after that, since I have a passion towards learning the digital circuits and other analog fundamentals, I took a post-graduation diploma in VLSI from CIDEC. And after that, I entered into a startup called as Unity5, and in that I worked on the different memory controllers like low power DDR4, low power DDR5 controllers. So my role is to design those controllers, write the code for them in the HDL designs, which we use Verilog or System Verilog. And similarly, at that time, my role is to verify them before the chip goes into production. And after that, I worked there for around 2.5 years, and after that, I moved on to Mindtree. So for that, from Mindtree, I worked into a client location into India, Malaysia, and there I worked around for around a year precisely, and while I worked on the emulation boards and different cryptography related projects. After that, I worked there for around 1.5 years, and I moved on to Sankalp Semiconductor, where I worked roughly around 1 year for a project related to that time the latest version of the ATMI protocol or ATMI 2.0. After Sankalp Semiconductor, I moved on to Intel, and there I worked for roughly around 4 years and executed projects related to 5G modem and graphics processing unit and the display controller. And after working in Intel for 4 years, I joined Samsung Semiconductor, and in Samsung I am currently there working for around 2.5 years, where my role is like a senior staff engineer, where I am currently leading and managing one of the IP of multimedia team. And my role is to manage the team, lead the team, design the test bench infrastructure to make sure that the integrated circuit is bug free and the quality is maintained, and before it goes for mass production, and also at the same time to ensure that much more testing and verification has been completed for that particular integrated circuit. So this is a brief introduction about me, and let's now start the presentation. Okay, so Industry 4.0. So it's also termed as the fourth industrial revolution. But before moving on to Industry 4.0, there are three other earlier revisions or the industry standards happened, that is the Industry 1.0, which came roughly around in the year of 1784 due to the machine which can be powered by either water or steam. So after that, we move on to the second industrial revolution, that is the Industry 2.0, roughly around the year 1870, which actually took place due to the innovation of electricity. And then finally, in 1969 or 1970s, during that time frame, we arrived at the Industry 3.0 due to automation, due to internet, then due to processor, laptops, and finally we are at the Industry 4.0. The term Industry 4.0 actually coined in the year 2011 in Germany as a part of their high-tech project. So what does precisely Industry 4.0 mean? Industry 4.0 are actually governed by the cyber physical system, which means one machine can interact with another without any kind of human intervention, so that the machine is itself intelligent enough to detect and rectify its failure, and also can collaborate with the other machine where no human intervention took place. So basically, how does this happen? So there are multiple technologies that help us to gain those kind of control over this Industry 4.0 standard. So some of the technologies are IoTs, artificial intelligence, like machine learning, deep learning, semiconductor and VLSI also comes in this area, big data analytics. All those combinedly form the Industry 4.0 revolution. So in this Industry 4.0, one more aspect comes into picture, that is the role of automation. Like the kind of mundane tasks or the routine tasks what we have in our daily life, how much we are able to automate those tasks, so that the human can perform the more complex tasks and the machine can do the automation on day-to-day basis. So all these combinedly form the Industry 4.0. Now, upcoming revolution which is there is already into picture, like the Industry 5.0. So in Industry 5.0, it's like a more collaborative effort between the humans and the machines. Like the innovation or the complex tasks should be carried out by the machines, and the more innovative and the complex tasks should be carried out by the humans, and the automated tasks should be carried out by the machines. So in that way, we are able to collaborate much more or interact much more with the machines in the Industry 5.0. But for that upskilling needs to be there for both humans and the machines. and they need to learn intelligently both from their previous experiences and also able to depict like how a particular system going to behave. So all these two industry revolutions are going to depict our future in the coming days, both in terms of Industry 4.0 and the 5.0 revolution. So like the next question comes like how teachers or how a particular individual can prepare themselves for the upcoming boom of Industry 4.0 and 5.0. So there are a couple of points mentioned, as you all can see, like what needs to be done. But before that, the first important thing is to explore multiple different areas. There is a popular concept known as the T concept. So what does it mean? So T concept means the vertical line refers to the mastery of one particular niche. Like somebody might be mastering, completing his preferences in artificial intelligence. Somebody has mastery in the subject like semiconductor. Someone has some other different passion towards a different particular field. So that vertical line refers to the mastery in the particular niche, and the horizontal line refers to the overview of the other different domains. So someone like, for example, in my case, apart from my semiconductor and VLSI, I have a different or a particular interest towards blockchain. So what will happen if we follow this T concept? When we explore multiple different areas, it provides a different outlook or broadens our outlook and provides a new perspective how we can look into a particular problem. So there is also a term called as a neuroplasticity. So it means our brain are formatted in a particular way in which the neurons will behave to achieve a particular problem. But when we explore multiple different areas, we stimulate our brain with multiple stimulus. And for that, the neurons are trained in a particular way to arrive at a problem in a much more different way. For example, let me try to give a different example. Few years back, like around 1.5 years back, I was writing a research paper. So I came about a problem statement. I was stuck with the problem statement. I tried to solve that problem couple of times but failed. Somehow, since I explored multiple different areas, I worked out a way from the machine learning technique and integrate into my semiconductor problem or the problem which I am facing that time. So I am able to solve that problem in a unique way. I thought that this is the only way how a problem can be solved, but I was wrong. Similarly, after a few months or like after 6 months or 7 months when I revisit the problem or after gaining some amount of experience when I revisit the problem, I am able to devise 2 more unique solutions out of it. So the point what I want to convey is that a problem can have multiple solutions, but which solution is perfect for the particular problem that we need to find out. And that can only be possible when we follow the T concept, that is the exploring multiple different areas apart from the niche in which we are specialized with. Similarly, the teachers should motivate the students in terms of their career guidance. Like if they want to pursue some other, like it may come in terms of first appearance, it might come in terms of a hobby. But that hobby might turn into a passion after coming years or months. So the teachers should always provide career guidance or like the important areas in which they need to understand or need to deal with their particular subject during that time. It could be anything, it could be of their interest, and I think the teachers should motivate themselves and the students to learn those different technologies. And the third thing what I believe is the upskilling. Continuous upskilling is required because since we live in such a era like where the things are changing constantly or things are changing very fast. So one technology which is valid today might get obsolete over a period of 1 or 2 years. So these are the few points which I believe like how the students can prepare themselves for this upcoming boom of Industry 5.0. We are already in Industry 4.0. 5.0 might be in the future and it might not be that much delay. It will come very much soon as we can anticipate that one. So yeah, so this is the categorization of overall Industry 4.0 and 5.0. Some points might not be there, but these are the overall precise definition. Mostly blockchain comes under Industry 5.0 because, and since I will talk about the different web technologies like Web 3.0, Web 4.0. So in that we will see how the different web revisions took place in the coming decentralization. Okay, so the first part is the VLSI and the semiconductor. So basically, what does the word VLSI mean? VLSI is called as a very large scale integration, which means millions of transistors are embedded into a single chip and like to form an integrated circuit. But the point is that what is the use of putting millions of transistors into a single chip? So if I tell a very simple term, for example, when we go to a market to buy smartphone, what are the first thing we are considering while buying a smartphone? That its battery life should be longer, its display quality should be fine, it should be smooth, the battery should not be drained out like in couple of hours. What is the processor? So all these things we consider while buying a smartphone. Similarly for laptops, what is the core, how much graphics is it, how much RAM, all those things we consider while buying a kind of a laptop or a CPU or like kind of a mobile phone. So all these things comes into picture when we embed those number of transistors into a single chip. That means what is the technology parameter? Previously, maybe 20-30 years back, we are working on 180 nanometer technology. Now the technology parameter is shrinking down day by day, years after years, and now it comes out to from 180 to 7 nanometer, and currently are moving on to 3 nanometer, 2 nanometer as well. So this shrinking of technology parameter means multiple more number of transistors are like embedding into a single chip. Because as we all know, Moore's law, that it tells like the number of transistors doubles after every 2 years. But now that statement is also getting false because the number of transistors are even getting double even 1.5 years or maybe less than that. So basically, if we go into the history of VLSI, it's not as straightforward as it seemed to be. In the earlier cases, maybe 30-40 years back, when the solid state devices is not into the picture like the BJT or the MOSFET, the current controlling element can occur through a vacuum tube. So vacuum tube is like a sealed glass tube inside which there is no air, and like the current controlling element is through two electrodes, that is the cathode and the anode. The cathode is producing the electrons and the anode capturing it. But the problem with such devices, it is very bulky and the power consumption is much more heavy. So the industry can't persist with vacuum tube because it is not feasible enough to move with the vacuum tubes in the future days. So after that, and moreover, vacuum tubes also work on the principle of thermionic emission. So when we talk about VLSI, it stands on three pillars. That is the power, speed and area. Every time when we design a circuit, we need to be concerned about these three factors. The power consumption should be as minimal as possible. Similarly with area, and the speed should be optimal or the speed should be fast enough. So when we move on to the solid state devices, that is the BJT or the transistor, so from there onwards, these different multiple technologies comes into picture, like the SSI, small scale integration, medium scale integration, then the large scale integration. As you can see, there are different transistor counts because these technologies, technology nodes can support until this much transistor count. For example, in SSI, only 10 transistors should be fitted in. Now, when we move on to the solid state devices, and the BJT was invented by Bratin, so like during that time frame, BJT has also different disadvantages. So the power consumption is lesser than the vacuum tube as compared to the vacuum tube, but it is not that much power healthy that it can be fitted into a circuit to form a large integrated circuit. So that time onwards, we move on to the MOSFET. MOSFET, as we know, is a 4-terminal device, body, drain, gate is there, as compared to the BJT, which is a 3-terminal device. So MOSFET's power consumption is much more lesser as compared to the BJT, and so we move on to the MOSFET with the VLSI technology. And currently, even through MOSFET we are moving on to the FinFET, where the transistors or the integrated circuit has been formed with the FinFET technology. So these are the different technology and the history of VLSI, how VLSI come into existence, and maybe in future years there have been talks that we move on to VLSI to ULSI, where the ultra scale large integration will take place, because day by day we are shrinking down the technology nodes and coming to a different practice, like where the technology parameter is less and we can build more and more transistor into a single chip. So now, since we are aware about the different software technologies like C, C++, Java, and how they are getting executed, but to code those VLSI related technology, we need separate kind of coding techniques. So those are called as the hardware coding, and it is like substantially different when you compare with the software, because the software coding's execution style and the hardware coding's execution style are completely different. Software codes executes sequentially, while hardware codes executes parallelly. So what does it mean? So hardware coding are by default concurrent in nature, and the software codes executes one statement sequentially, one by one. Moreover, the software code doesn't need to be aware of the memory requirement of the circuit, the timing delay of the circuit, or the clocks or the reset. But while designing the hardware codes, we need to be aware of those kind of parameters, like how much is the memory consumption, how much is the timing requirement, how much is the clock requirement, frequency requirement. All those things we need to consider while designing the hardware coding. So, like for that, there are different HDL based codes, that is the hardware description language comes into picture to model those hardware based coding. Some of them are VHDL, Verilog, and now the industry has already moved from those parameters or the technologies, and the industry is now using something called as an HDVL, that is the hardware description and verification language, which can be used as a both designing language and a verification language, that is system Verilog. So now there are in the market, there are multiple other different open source languages which are being used for coding those RTL design or the HDL based coding, which I will describe in the later part of the slide. So the overall VLSI is subdivided into these two different sections, that is the front end and the back end. The front end is comprising of this RTL design and the RTL verification. The acronym RTL stands for Register Transfer Level. So what does it actually mean? So RTL design means modeling or designing a digital circuit with the help of the HDL based languages, as I described earlier, that is VHDL, Verilog or system Verilog. So while modeling those digital circuits, we need to be also aware of the fact that it should be synthesizable. What does synthesizable mean? Synthesizable means it should be fitted into a hardware. If it doesn't, that particular code doesn't fit into a hardware, it doesn't make any sense. So how to ensure that the circuit should be synthesizable? So there are different constructs or keywords. Similarly, while learning the C language also, we need to be aware of certain construct, which we defines the language definition. Similarly here in RTL design, while coding the RTL based models using the HDL languages, we need to be aware of certain construct which needs to be inputted into the code to make sure that the design is synthesizable, that it needs to be fit into the hardware. So for example, there are certain guidelines, I am explaining one or two. So for example, you can't use delay into the circuit, you can't use wait statement which is used for delay, looping construct, all those things need to be not possible while designing this RTL design. But for RTL verification, there is no such requirement. We can design a behavioral model as per our wish to make sure that the RTL design is meeting the expectation. So what does RTL verification mean? In simple terms, RTL verification means like if the RTL is also termed as industry as DUT, that is the design under test. I am providing a stimulus, input stimulus to the DUT, and I need to check the output behavior. The the output be between the input and the output, there should be a checker which will make sure that the design is meeting as per the expected specification and there are no errors, there are no bugs within the design. Because if there is a silicon bug or like the bug in the terms like the design is not behaving as per the expected specification, that could cost millions of rupees and even the project can be cancelled. So while doing the RTL verification, we need to be ensured that the RTL design is behaving as per the expected standard or whatever is working principle, it should work as per the expected specification. Similarly, we have backend. Backend comprises of mainly these two terminology, that is the physical design and the custom design. Physical design refers to the layout, the floor planning, how the chip will be fitted, how the blocks interconnection between the, it's at the physical level. Like what is the different interconnection between the cells and the block, all those comes into the physical design. Similarly, the custom design, in the custom design we have memory characterization. I'll explain in the later part of the slide the exact categorization of VLSI and what are the different opportunities. So like there are different memory related areas, IO characterization, input, output, all those things come into the custom design part. So this is how the overall VLSI precisely looks like. First is divided into front end and the back end. The front end is again categorized into RTL design and verification, and the back end is again physical design and the custom design. So the front end part mostly deals with the coding of the like the digital circuit. Its verification. Verification again deals with separate sort of coding languages are there. In the back end, it's mostly the design. It's mostly the analog part. Mostly like how we can anticipate the design, like what is the metal length layer. All those things comes into the back end part. Where the most CMOS related knowledge, the analog fundamental knowledge is required for this second section. Okay. So now the first subdivision. So RTL design. What this IP design and SoC design means. So in simple terms, we can think of, for example, we are sitting in this classroom. So this classroom is one of the building blocks of this whole college. So this we can think of as like an IP. That is the intellectual property or a basic building blocks of a design. Similarly, beside this classroom, there is a one more section. Beside this, there is one more section. All these combine a subsystem. When multiple IPs integrated together, they form a subsystem. And when all these subsystems integrated together, they form an SoC. So you can think of this whole college as an SoC, each floor as a subsystem, and within each floor, each section is an IP. So basically, the SoC is the top level view and the IP is the lower level, that is the basic building block of the design. So when we talk about this RTL design, is basically or a RTL design engineer, when he enter into the industry, he needs to perform this kind of activities. So RTL design is the core area. If particular engineer is assigned with that particular area, what his role? His role is to understand the specification, design the circuit, like designing the circuit in terms of coding. Like he can like start with a basic module. He can subdivide the entire specification into different module. Each module he can start designing with the coding languages like either VHDL. VHDL is nowadays anyway obsolete, like Verilog or System Verilog. And then he needs to integrate those particular IP-based design. Similarly, he needs to be also concerned with the static timing analysis. Now, what does static timing analysis mean? So basically, in digital circuit, in engineering days or anywhere, we comes up with the terms like setup time, hold time, metastability issues. So all those things need to be considered while doing the static timing analysis check. So the first thing what he needs to consider, or a particular engineer needs to consider, that there should not be metastable issues, like the particular output is settling down to a logic level, either 1 or 0, or it's like a defined input, defined output. It should not be toggling between 1 and 0. So that metastability issue needs to check. The setup time is meeting or not, the hold time is meeting or not. There are multiple other different parameters like clock skew, whether I am getting the clock from the two different clocks, there is a delay or not, there should be no data loss, there should be no data incoherency. So all those things need to be checked. Similarly for clock domain crossing as well, while two clocks or the read clock and the write clock are from two different clocks, like domains, all those things we also need to check. Similarly, a synthesis engineer needs to be dealing with the synthesis part, like after designing the code, he needs to pass that code along with the library information into a synthesis tool. That synthesis tool will generate a netlist. I describe in detail how the synthesis flow will look like in the later part of the slide. In the design for test, that particular engineer needs to check whether like any particular flip-flop or any particular like synchronizer has any unconnected input or not. So all those things you need to be aware while going through this kind of check. Link superlink is again a separate tool which will ensure any kind of floating signals are there or not. So all these are 5 or 6 major roles what an RTL design engineer can get or like can able to work while he work like enter into an industry. Similarly for RTL verification, as I mentioned, similar to RTL design, there are also 3 different areas like SOC verification, IQ verification and subsystem verification. And there are multiple different roles in the RTL verification as well. Among them, the most common and the most prominent role is the functional verification. So functional verification deals with verifying the integrity of the RTL design, like whether everything is working perfectly or not. For example, if I take an example of a memory controller, what is the role of a memory controller? What I am writing, I am able to read it back or not. This is a basic check. So whether I am able to do that check or not, so further functional verification is there. So I need to write a test scenario and need to check whatever I am writing, I am reading it back or not. The clocks are behaving perfectly or not. The results are behaving perfectly or not. So all those functional related checks, like for example, take any protocol like I2S, SPI, like that we have like ARM-based processors. So everything is there. Like functional verification deals with those kind of checks. Similarly, we have coverage-driven verification. When we sign off a chip, we need to be ensured that the coverage is complete. So coverage is nothing but a metric which will decide the sign off of the verification process. So for example, there are 2 different kinds of coverage verification. One is code coverage and other one is functional coverage. Code coverage defines how many lines of code or how many percentage of RTL design code has been accessed or has been covered. It doesn't care about the functionality, it only checks how much percentage the RTL designer has been covered. For example, if I write a if statement, if and else statement, the code coverage will tell me whether both the if part and the else part has been covered or not. If due to some reason or due to some bug within the design, the if part is not getting covered, so those coverage metrics helps me to decode those kind of bugs. Why this if part or else part or a particular case statement is not getting covered. So then the verification engineer with a discussion needs to come up with a discussion with the RTL design engineer whether there is a loophole within the code or not, and he needs to write a specific scenario to cover that if condition or an else condition. Those are called as a directed scenario. So until and unless code coverage is 100%, we can't move on to the next stage. Similarly, we have functional coverage. Functional coverage deals with the functionality. So we need to write separate bins or the functional bins which will decide the functionality of the RTL design. That is how much functionally RTL design has been verified. Like for example, if I take an example of any example like maybe FIFO or any sort of memory controller. So there could be multiple aspects of verifying a memory controller. There could be address decoding issues comes into picture. If I am writing onto a particular address, it is reading from a different address apart from that particular address. So how we encounter all those kind of scenarios? So for that functional coverage will gives me a percentage like, okay, this much functionality RTL has been verified, but the RTL designer has missed out on some functionality which he needs to put into the RTL code. So similarly, if functional coverage is not 100%, we can't move ahead with the next stage. Similarly, we have register verification. So for example, as I given an example of SOC verification, which we can think of our entire college as an SOC, and the IP is the basic building block for example, this floor. I need to check an interconnection from the top floor to this floor. So from the top floor, while traveling from the top floor to this floor, I need to come up with multiple stairs or the lift. So whether that particular connectivity has been properly maintained or not, these are checked with the register verification. So register verification will travel from the top level to the basic building block and will check that the connectivity or the interconnectivity or the integration between the IP and the SOC is properly maintained or not. So in this way, we ensure that the whole connectivity of an SOC or a system on chip is being properly built and there are no issues with my design. Similarly, there are different kinds of checks like the assertion-based verification. So assertion-based verification helps us to improve the observation or the debug process in my verification. So how it will do? So for example, if I write a test scenario and due to a bug within the RTL design or a defect within the RTL design, my test scenario failed. So if that particular test scenario failed, the basic or the first rule as a verification engineer, what I need to do, I need to open the waveform or the log, failing log. I need to check at which portion that particular fail happened, and then I need to trace through the waveform to find out the root cause of that particular failure. But this assertion-based verification helped me to reduce the debug effort. So how it does, it puts some insertion like kind of in the RTL design, there are some specific areas like from the RTL design to verification, there is an interface. So that interface provides me the logical I/O connection between the RTL design and the verification. I need to provide some check within those interface monitors or the checkers. So that will continuously monitoring the RTL design. Because the nature of assertion is that assertions are by default on. So if any particular failure happens, that will be able to debug even before the test is ends. So in that way, we are able to decide whether my verification is complete and even there are any bugs in the RTL design. Similarly, there are other verification techniques like low power verification, which will deal with the different power domains, clock domains. Basically, in general, in SOC, there are multiple like there is not a design exists in the industry currently which works on a single clock. So there could be multiple clocks. So whatever the voltage parameter, what is the power consumption, power domain, so all those things comes under low power verification. Similarly, there are C model and DPI verification. So what does it mean? So IP verification and subsystem verification, we can deal with the verification languages like UVM, that is the universal verification methodology, system Verilog. But while dealing with the SOC verification, which is much more closer to the processor, I need to write the scenario with the C language. Now, UVM as a hardware language can't understand the language of C. So to interact between C programming and the UVM based methodology, I need some mediator to convert those hardware based languages to make it understandable to the C language. For that we have DPI, direct programmable interface. It will act as a bridge between the C model or the C based verification and the UVM based verification. Similarly, we have graphics processing verifications and CPU based verification. All these verification are achieved through the C. So in simple words, if I want to summarize, IP verification and the subsystem verification, we need to write the verification models or the verification behavioral model either using Verilog, either using UVM or system Verilog, but the SOC verification should always be performed with the C language since it is much more closer to the processor and it can't understand the raw level language details of the IP and the subsystem. Now we have the custom design.
So once this RTL design and the RTL verification complete, that is done, my front end design or the front end part of the VLSI is over. Now I am moving to the second part, that is the back end part. And in the back end part, that's how the custom design and the physical design comes into picture. So here custom design is mostly concerned with the memory design, IO design. So there are different levels of checks. Like in CMOS, basically when we learn in CMOS, we come up with something called as stick diagrams or like the kind of metal layer checks. So all those things are being performed here physically using the tools, using those custom design and the physical design. So this part deals with the analog layout, analog design, how much spacing is required between one layer to the second layer, the DRC checks, that is the design rule check, the LBS checks, low voltage checks, all those checks will come under the custom design part. And DFT is kind of a bridge between the front end and the back end. Like both, it can perform in front end as well as back end as well, because it's kind of a ATPG. ATPG is like an automated test pattern generation. So it induce some kind of logic into my RTL design, which will check there are unconnected inputs within the flip-flop or not, or the flip-flops or the resistors are properly connected. So all those things need to be performed while doing the custom design part or the back-end design. And here is the traditional flow. This is just a basic flow of how the RTL design, RTL verification, physical design and the custom design works. Why I put this flow? Because this flow is more or less like maintained by every industry, every company whenever they are signing off the chip. This is the mandatory flow which any company in this world has to maintain and needs to go through. So the first part comes is the design specification. So what does design specification mean? So design specification means a market requirement. So for example, tomorrow I need to devise a Samsung new model or an Intel new processor, like after i9 I need 2 model or something kind of new different core processor. A requirement comes into the market. So out of this requirement there is a design specification which is also called as the microarchitecture specification. So in that microarchitecture specification, not complete details but overall details has been provided how my particular system or like a kind of a the kind of design looks like. It provides the details about the frequency requirement, it provides the details about the IO requirement, input output, it provides the detail about the maximum frequency requirement, the working principle, not in very detail, but the crisp details will be there. So out of this microarchitecture specification, the RTL design engineer, out of his intuition and out of his knowledge, prepare a separate document which is called as a design document. And in the design document, he puts all the internal details as per his knowledge, as per his experience, as per going through the design specification. Similarly, that document is given to verification engineer as well. So RTL designer is preparing his designing on the terms of this design specification. The verification engineer is also building his verification models to test that RTL design after reading that particular design specification. So now the first part comes the design entry. That is the how an RTL design needs to start, or like how he can start, or a particular person can start after reading the design specification. So here is the design entry. Before, like maybe 50 years back or 40 years back, where we don't have any coding languages like today we have Verilog, ATAL to code the RTL based design. So during that time we don't have any HDL based designs. So the designer needs to put the design entry using the graphical user interface, that is with the help of the schematic sheet, where we have the symbols of basic dates and the flip-flop. Then the symbols need to be dragged onto the sheet and then need to be put into the using the primitive cell into the design entry tool. But now today the system is changed. We have much more automated techniques in the terms of coding languages like Verilog and VHDL. So a design engineer, after reading the specification, start writing the code and then divide the code into separate modules. For example, in a particular SoC or a system on chip, I can have a multiple module. I have an I2S protocol also. I could have a separate memory controller. I could have a low power memory controller. Different modules are there. And inside the different module, I could have a separate sub modules. So the design engineer starts writing those modules and after the design is completed, he needs to stitch those modules to form the top level design. Similarly, once this design is completed, either using any one of these coding languages or the ATAL languages, the functional verification starts. So in the functional verification, we need to check, again as I said in my earlier slide, we need to check if it's functionally verified or not. So if it is functionally correct, we can move on to the next stage. If there are any issues, then we need to move back to the second stage again, that is the design entry. And we need to inform the RTL designer, and everything we can't say it like verbally or like communicated in person. For that, there are also different separate kind of tools. We need to raise the issue, those be different from company to company. Each company has their own separate set of tools to raise those issues, and we need to inform the RTL design engineer that okay, this is the issue, this you need to solve. Sometimes it might happen that it might not turn out to be an RTL design issue. It might turn out to be a verification engineer's own mistake as well. He not able to understand the design specification correctly. So it can happen both way in an RTL design issue. If it is an RTL design issue, it needs to be rectified at any cost. And if it's a functional verification issue, then also we can move on to the next stage because the verification can work in the background as well. So once it is functionally correct, the main thing is that it should be functionally correct. So once it is functionally correct, we need to move on to the logic synthesis. So the logic synthesis is the part which gives me a netlist or like kind of a file on which the entire design information is there. So how it happened? It happened in 3 stages: the translate, optimize, and mapping. So once the RTL design is complete, the input to the synthesis tool are the RTL files, the library information, and the technological parameter information. All these are fed into the logic synthesis tool, and out of it, it produced me an unoptimized Boolean description. What is an unoptimized Boolean description? Unoptimized Boolean description, you can think of it's a large expression in the form of SOP or POS expression. So in digital circuit, while running those digital circuit, we used to have K-map, Quinn-McCluskey method, espresso method to reduce a digital expression and to make it more optimized. Similarly, we don't have those K-map or all in the terms of the languages or the tools, but the tool uses its own technique to reduce those digital expressions. So when it in the translate stage, when the logic synthesis produce me and like kind of an unoptimized Boolean description, it is something which is not controlled by the user. It is not in our hands to optimize the Boolean description or unoptimized. But in the optimized process or the optimized stage, we have the control over that unoptimized Boolean description to make it optimized. So for that, we have 2 processes. One is flattening and the other one is factoring. Both are opposite to each other. For example, if I have a large process or a large expression, I need to factor it, and I need to factor it in such a way so that keeping the power consumption, keeping the gate count in mind, because more the number of gates, more the number of power consumption it will be. So keeping that in mind, I need to optimize it in a way that it consumes more number of gates, it consumes less number of gates, it consumes less number of logical expression. Once this is done, then the mapping process starts. The mapping process means how that particular logical expression can be optimized to gates. So for that, we can take the help of technology library also. In the technology library, there are multiple expressions or primitive gate information is there, which we can take the help and we can map it. Once this is done, a netlist is produced. So with the help of this netlist, we move on to the next stage. That is the timing analysis part. So, yeah.
Please explain flattening and factoring.
Yeah. So like factoring. So factoring, it means like for example, if you have an SOP expression. So generally we use in our normal days, like what we use K-map to optimize that expression. Similarly, the tool use the factoring process. So factoring is breaking down a particular expression into a small subset. So for example, x equal to y or b and some large expression is there. So we need to factor it down into multiple subsets in such a way that the gate count is less or the number of logical expression is less. So in that way, if we factor it down, so we are ensuring that the power consumption in a way indirectly by power consumption is also less. So that's how the factoring process works. Flattening is the opposite of the factoring. Sometimes what happens if I get an expression in the form of a factored form and it is too much factored that I can think of binding two expressions together that again consume less number of gate information or less number of logical expression, then I need to go to the flattening. Both are opposite to each other.
What kind of tool is used for that?
So this is the logic synthesis tool. So the tool they are using for the logic synthesis purpose after the functional verification.
Maybe some kinds of simulation tool is utilized.
Simulation tool, yeah. So like I'm not sure about the logic synthesis tool because after my job is as a functional verification engineer. After the verification is complete.
In itself there are logic synthesis tools.
Which one?
So in itself there is logic synthesis part.
Yeah, logic synthesis as a
That part will be used or
yeah, in the logic synthesis tool, see the first part when the translate process happened, it will give me an unoptimized expression. So after the unoptimized expression, when it produces the unoptimized expression, it is not user controllable. But after that, with the help of the tool and with the help of the technique, coding technique, you can optimize that expression and feed it into the tool again. So that will generate me a netlist out of it. So like we have cadence tool, we have synopsis tool for that purposes. For simulation, like for example, we are using like VCS, NCC, all those kind of tools we are using for modeling those kind of different techniques and generate the netlist out of it. So once the netlist got generated, we need to ensure that the timing analysis check needs to be performed. So the timing analysis check, like as I earlier mentioned, the setup time, the hold time, metastability, clock skew, slew, propagation delay, contamination delay, all those kind of check, the timing analysis engineer needs to be ensured so that there is no data loss. For example, a typical case of a data loss, if two clocks are working at two different frequencies, so if there might be possible there could be a data loss when I am moving from a faster clock domain to a slower clock. So all those kind of check needs to be performed in the STA checks, and after that we have the design for test to check the automated test pattern generation, and again a pre-layout simulation. In the pre-layout simulation we are again testing backtracking it back that everything is perfect. If everything is perfect, we move on to the floor training stage. So from there, actually backend starts from here itself. So there until this point the front end work mostly completed. So after that we are just moving on to the backend. And floor planning is just to define the shape of each subcircuit module and the kind of connections within the block, and it also checks if any delay is being introduced, we can minimize the delay or not. All this kind of check has been introduced within the floor plan. And there are multiple tools are there, the tool or the synopsis tools are there to take care of those things. And in the basement, we are just making the logical interconnection between the cells and the block. Routing means which path is better to make those interconnection. And after that, in the circuit extraction, we are extracting out the RLC parameters, and it produces me a file called as the SPEF, that is the standard circuit exchange format. So from that, the circuit extraction, I am extracting out the parasites, and finally it goes on to the post-layout simulation and in the fabrication. In the fabrication part, it's again subdivided into multiple different, because that's what happened in the foundry. People used to wear the bunny suit and then used to enter into a room, and where everything needs to be maintained, that no dust particles, optimal temperature, where they're fabricating out the chip. So out of this complete ASIC flow, the final format that is being generated is the GDS format, which we might be need to be concerned with. And after that, if by any chance anything happened or any bugs comes into picture after the post silicon validation, then we need to do the ECO check, that is the engineering change order. So you can think of it's like kind of a when before FPGA, when we are working on the CPLD boards, we are doing kind of a molding or kind of to change the wiring and the jumping things. So all those things need to be done to change the wiring connection to modify the bug in the engineering change order. but that is the last thing that an ASIC engineer needs to be in his design, because that's hamper the design quality and the overall production. So this is how a typical ASIC flow looks like. This is the very basic flow, because in between there are multiple intermediary stages. Like in functional verification itself, there are multiple stages. On RTL design itself, there are multiple different stages where an engineer needs to deal with. But this is how precisely it looks like. Even the backend part also, there are multiple other different things, but this is the basic flow a particular ASIC engineer and front-end engineer needs to follow when doing the kind of RTL design analysis.
So ECU will be done after fabrication or before fabrication?
So kind of it depends, like basically after the post silicon validation. So basically when the floor planning and the backend process end, so we have a post silicon validation as well. So after in between that post silicon validation, if any bug comes out to be in the picture, then also we need to do the ECO checks as well. So that depends on the number of the complexity or the nature of the bug. If the bug is too minimal, for example, if the bug is like a register based bug, for example, in registers we have different attributes: read write, read only, write only, or kind of there are some special registers like after writing 3 times it will reset. So if there is a bug in the status bit of the register, so for example, if it is not reading the status bit, sometimes depending on the nature of the project we can keep low. But if the bug is too much complex or too much important to solve, then only we need to go to the ECO checks. Otherwise, that is not feasible enough, because that to fix that bug, it might hamper some other part of the design. So we need to be concerned about what we are fixing and what is the nature of the bug we are fixing.
Customized. I mean, some sections of the design may be utilized for the purpose of ECO checking, and some portion may not. It depends based on some section of the.
Correct. So basically, that's what, as a verification engineer or as an RTL design engineer, it always needs to be checked. Like as I earlier mentioned in the verification part also. So apart from those coverage and the coverage metrics, we need to be continuously talking with the RTL design engineer. Is there any gap? So we need to be 100% sure. This is the last thing that a designer or an engineer should anticipate. Before that, we should be 100% sure that everything needs to be closed. So as you said, if I am fixing that particular thing, I also need to be sure that the other things are not broken. So sometimes it increases the time to market as well, because I need to perform some part of the verification or the regression again, which consume a hell lot of time. So basically, we need to ensure, and it's actually not depend on particular project as well. It depends on what the customer like intent in his project. Like in some kind of automotive section, where a particular life is at stake, because now VLSI industry is moving on to the automotive sector as well. So during that time frame, it is critical to address those kind of issues. So during that time, we need to understand the nature of the issues and need to perform that particular section ECO.
Can you give some that area that where the automation, which section the automation is being included in the VLSI?
Automation. So automation, basically in the functional verification part, we are using the maximum portion of the automation, and in the backend part. So in the functional verification, I will give an example. For example, there could be thousands and thousands of test cases to decide the quality of an RTL design. So there could be multiple number of test cases. Could be directed test cases, could be random test cases. So for example, directed test cases, what the verification engineer can anticipate. Like he thinks that the RTL design should behave in this particular way as per the expected specification. So I need to write this 5 directed test case first to check the quality of the RTL design. So after writing those directed test case, the verification engineer move on to the random test case. But the random scenarios is not in his control. So for example, for that random scenarios, there might be multiple number of seed. So what happens? So when I'm running the random test cases, it might produce a bug within the RTL design because it hit in that particular exact area where the directed test cases can't hit. So for this kind of random test cases, we can take the help of the automation. We can write multiple scripts. We can take the help of the machine learning as well to train it with large number of data set, to train it in such a way that it can understand the design better. We can use the Python script as well to reduce our simulation and the runtime, so that after compiling the design, it start automatic the test cases. In the regression management, we can use the maximum help of the automation. Like, because in regression management we are dealing with more number of test cases at a particular time. So how the regression needs to be managed. For example, there is a critical case. For example, when you run a regression with multiple different seed, for example 500 seed. In the earlier days of tool, what might happen when you are running 500 seed, you might be sure, or you might convince yourself that you are running that particular scenario with 500 different unique seeds. But sometimes what happens, one or two seeds repeat. So out of 500 seeds, you might be actually running 498 seeds. So in those cases, we can use the help of the scripts to remove that unwanted seed out of it, and it can run 500 different unique seeds. So there are multiple different areas where we can use automation within the functional verification part. So similarly for the backend, they also need to work with multiple different flows. So they are actually using the Perl script to automate their flows. Similarly in functional verification, we are also using script to automate our flows.
Sir, I have a question. So during the optimized phase of logic synthesis, as you mentioned that this factoring and flattening operations are there, there's the results, right? Then who to decide when to go for factoring or when to go for flattening? Is it the design engineer or is it done automatically?
Yeah, so it's like a collaborative effort. So basically, in like kind of the role when you are given, it's highly unlikely that an RTL designer, along with an RTL designer, someone given a specific role only to logic synthesis. So basically, it's in the control of RTL design engineer only, because functional verification engineer can't do anything out of it. So the RTL design engineer has to take the call first, because he is the actual one who needs to decide that whether factoring is actually minimizing the gate count.
That means manual intervention, no machine.
No, tool is there. Tool is there to take care of it, but you have to take care out of your intelligence, like
So
what to.
that is human intelligence, not artificial.
Nowadays, machine learning techniques are coming, but as of now, it's the first design engineer's call whether he needs to optimize that with flattening or factoring. After that, the machine will do that same.
So one thing I want to know that is when you prepare the next list, the data that I will get, the expression, that has to be I have to keep it the optimized from the next list, or the unoptimized form I have to convert it.
No, unoptimized thing is not in your control. What the tool will generate for you is not in your control. So it will give you some expression which needs to be optimized. There is nothing like that. It is not intelligent enough that it will optimize by itself and it will give you an expression out of it. So for the tool
Factoring I can control optimize.
it could be, see, factoring, flattening, I have mentioned, it's like two basic techniques. There are multiple other techniques which needs to be employed, and these needs to be considered by the RTL design engineer. So what needs to be done? Sometimes if the expression the particular like this translate mechanism provides, it might be an unoptimized expression. But if the RTL design engineer thinks that to optimize that expression, I need to take a monumentous effort, so he might skip that one at that particular point. Because anyway, when you're going to the timing analysis check and the other check, at the float plan again is anyway going to be checked, like whether I am kind of anyway can reduce the delay or the frequency requirement of the circuit or not. So all those things will come into picture. So it depends on the project by project basis, but yeah, this is the ideal two techniques which people generally use. But apart from that, there are multiple other techniques.
By these two techniques, we can convert the unoptimized.
Correct.
Because if we come to the design for test, then if the data is unoptimized because it is consume more power or more gate consumption.
Yeah, so anyway, in the design for test, again, when you are doing this ATPG generation, it will again check like the flip-flops are interconnected properly or not, whether any X propagation is there or not. If there is any X or Z, like that anyway, he needs to revisit, like he needs to check the entire thing into the like the tool, the DFT tool, he needs to check like whether any unconnected signals are there or not. So this is one more flow, but generally the industry or the big scale when the mass production or like required or the design frequency size is big, we are not using this flow because these are used generally for the lower frequency requirement and if the design is small. So yeah, so anyway it's more or less same. Only the file format which are being produced in the implementing design, that is the translate, map and base and route are different. There is the NGD stands for native generic description. UCF consists of user constraint file, that is again the timing analysis and all those things are being performed. NCD native circuit description file. Otherwise, until timing analysis is more or less same. In the device programming, only in FPGA, we are putting the design into an FPGA board. It could be Kintex, it could be Xilinx board or any board like Zinc board as well. When we are checking that particular design is being fitted into the hardware or not. And the file that has been produced out of the device programming is the .bit file, which an FPGA engineer needs to be concerned with. But in the industry, currently in industry, very few industry is currently using this FPGA flow because, as I said, the complexity level, the frequency requirement that industry needs can't be fitted into an FPGA flow. Okay, so like this is how the different phases of an ASIC verification looks like. So as I earlier mentioned, the input we need to feed to the DOT, and out of it we need to check the output, how the output is behaving as per the expected specification standard or not. So for that we have the checking mechanism. So basically, like similarly to the RTL design, the verification engineer also needs to first start with the specification, and after going through the specification he needs to perform some documentation work before the actual coding starts. First of all, the main documentation work is the feature plan. It could be in a form of an Excel sheet or could be anything as per that particular verification engineer. So the feature plan decides the number of features I need to verify for the particular verification. So what is that? Like for example, depending on a protocol, let's say I4 or I2S or an AMBA protocol like AHV, AXI. So what are the number of features a particular verification engineer needs to verify? All this needs to be documented in the feature plan. Then comes the verification plan. So, or it could be otherwise, verification plan also can come first, not an issue. So in the verification plan, he needs to decide or he needs to rework like how my test bench infrastructure should look like. So basically, in a typical UVM or a system Verilog based testing infrastructure, there are multiple components like driver, which will drive the stimulus onto the DUT. The monitor will check the transaction is perfect or not. The monitor again will revisit or like reconfirm the transaction into the scoreboard. The scoreboard is the area where the actual checking mechanism takes place. So all those infrastructure based thing or all those kind of thinking needs to be documented into the verification plan. So the verification plan actually consists of the whole test bench infrastructure, how the flow looks like or how the verification flow for the verifying the particular RTL design looks like. And after the verification flow, he needs to come up with a test plan. So the test plan is a subset of the feature plan, wherein verification engineer needs to come up with a test scenario to decide the quality of the RTL design or whether any bug is sitting or hiding within my design or not. So for that, the verification engineer needs to prepare a test plan, and this test plan are the directed test plan. Directed test plan means, as I earlier told, what the verification engineer can only anticipate or think of. Like these are the areas which I need to verify, because there are multiple different test planning techniques are there, like directed testing, random testing, stress testing is also there. Then there are corner case scenarios are also there. So corner case scenario comes into picture. For example, you run the regression or for days after days. So for example, to check if one single scenario you run it with 10,000 seed. After 10,000 seed you get a failure. So it's an exceptional case, because generally when you run a test for 10,000 times and if it passes, generally that particular scenario passed. So if that fails at that point, at first instance we might think of like it's an RTL design issue, but it could be an issue at our test bench also, how the infrastructure has been built. So we need to first check that one. So once this is done, so we can move on to the other things. So this, until this point from the specification to the test plan, it is all documentation work what verification engineer need to come up with. After that, the actual coding starts. So after the test plan, we need to start the building the UVM behavioral model or the test bench. So the thing, oh, let me check if I put that slide or not. So basically, what he needs to come up with. So when I'll take after this first portion gets complete, I'll take a 5 minutes. So once this, so after this test plan, he needs to start building the UVM based infrastructure. So basically, the UVM based infrastructure, the first step is to understand the I/O. So whatever the I/O is there, we need to put it into the interface. So once I put it into the interface, I have a clear understanding how my input-output port behave. The next comes the driver model. In the driver model, I am actually interacting with the RTL design as a pin level. So whether my pin level activity is performed or not is checked through the driver. So the driver has a handshaking mechanism with the sequencer, but the sequencer is actually getting the sequence item as a stimulus to the driver to put it into the duty to check. The monitor receive it and put it into the scoreboard, and the scoreboard is where the actual evaluation mechanism happens between the whole UVM test bench or the system Verilog test bench infrastructure. But now, once this verification complete, once this test planning is complete, once this execution is also complete, initially it's very easy to catch the bugs because those are very low hanging fruits. But once the bug rate chart, the verification engineer also needs to maintain something called as the bug rate chart. So once this bug rate chart starts dropping, or after the random test cases or the directed test cases, I am not able to catch any more number of bugs, then the coverage comes into picture. So then we need to initiate the code coverage and the functional coverage. And as I earlier told, both needs to be 100% to move on to the next stage, that is the backend stage. So once this code coverage and functional coverage I perform, and there is an exclusion file. Exclusion file means we need to get it from the RTL design engineer. That means the dead code. As I earlier mentioned, the code coverage will define in the if-else condition whether I am executing only the if part, else part, or both. But if the design engineer says that okay, you don't need to execute the if part because this is a dead code and it might not require for you to cover, so he will exclude that from the design, and that exclusion file we need to put it into our tool. Generally for covering we have separate tools of like the IMC tool, the B manager tool are there, which are currently much more intelligent enough to decide that kind of flow. Sometimes the RTL design engineer, if he is new into a design, he might not be able to tell, or if it's a legacy based design, someone doesn't want to hamper that design. So the RTL design engineer himself might not know whether it's a dead code or not. So for that, the V manager tool now comes up with a UNR based technique which will run through the entire design, and by through its own machine learning technique, it can anticipate whether it's a dead code or not. If it finds a dead code, it will automatically exclude that part from the design, which makes the work of a verification engineer much more easier. Then comes the XPROP plan. In the XPROP plan, we are again inducing XPROP, or it's kind of a negative check. We are inducing XPROP by ourselves to check if there are any XPropagation coming out of my design from any unconnected or connected input or output. So once this is done, once the XPROP is 100%, coverage is 100%, functional coverage, code coverage is 100%, bug rate chart is 0, the conversation with the RTL design engineer, the test plan is reviewed, the verification plan is reviewed, then I go for the sign-off process. So once the sign-off process completes, then the other process or the other activities within the VLSI will start. So these are some of the different technologies. Till now I only talked about VHDL, Verilog, and System Verilog and UVM, which are primarily being used as a verification language in today's industrial scenario. But this, not only this, there are other verification languages out in the market which are open source to enable an engineer who has a passion for learning verification, he or she can do so with those kind of languages. For example, we have Python. Python is an open source verification language and it has been invented specifically first for the software engineers who is a passion to enter into the VLSI industry. So it will enable a software engineer in such a way that he can also write the verification models or the code verification models with the help of something called as a CocoDB. CocoDB is a library enabled in the CocoDB is a module enabled in the Python called as a PyUVM. So PyUVM is a library which will enable me to replicate the UVM or the System Verilog based behavior within a Python based test bench. It's completely open source. Currently, the GitHub community of, I think, many engineers, I don't know the count, so they are maintaining that page. It's everything downloadable. It's completely open source. The problem with those kind of technique, as of now, the industry support is not that up to the mark as it's supposed to be for Verilog or UVM or VMM. Currently, the tool that supports CocoDB or the open source languages are Icarus, which is also itself an open source language, or a Verilator, which is also an open source. So those are the two simulators which are currently supports the Python-based adventure. The other industry-based simulators like BCS, Verdi, NCC, all those are not supporting that much the Python-based adventures. Similarly, we have something called as a PSS. It's actually maintained by all the EDA companies like Synopsys, Cadence, and Siemens. In VLSI, these are the three EDA companies. So they are building the tools. So PSS is being has been already built by these three companies. So what it will do, it will generate an intelligent model. It has a machine learning algorithm embedded inside it. So it builds an algorithm which will anticipate me multiple different test scenarios to decide the quality of the RTL design. Obviously, it's not a replacement for UVM and System Verilog because the kind of details UVM can anticipate the PSS card is like kind of a wrapper on the top of UVM so that I can offload some of my constraint or some of my test scenario to the PSS. SV unit is again an open source language, GitHub community is maintaining it. So like is actually invented to facilitate the verification engineer so that can do the testing at the unit level, or it can be used for the RTL design engineer as well. Previously, if RTL design engineer has written a code, he don't have the support until he write the full code to test it. But SV unit enables it and both an RTL design engineer and verification engineer to do the testing at an initial level whether that particular module is working or not. Similarly, since VHDL is getting obsolete day by day, so the GitHub community or the freelancers comes up with the different techniques like OSVBM or UVBM to support the VHDL. Because if you go to UK or some kind of defense companies, people are still using VHDL. They have not migrated from VHDL to the Verilog. So they are using the old technology till now. So, but VHDL support is day by day getting weaker. So people comes up with these two different methodologies. There is the OSVBM and UVBM, so that the designs which are still now in VHDL can be verified using those two technologies. FUSA is a functional safety architecture for the automotive. As I told that the VLSI chips are nowadays going into the automotive industry, into the different cars, are using the for the ADAS based technique and like radar based technique, like self-driving cars. So they are using all the VLSI chips for that, and this functional safety architecture for that only. So the functional verification can only decide the quality of the RTL design whether it's functionally verified or not. But the functional safety architecture or the architecture will decide whether a particular design or an RTL design has the capability to detect its failure and also has the capability to rectify it by itself. So those kind of architecture has been decided by the FUSA, that is the functional safety architecture. And tickle part, there are some other languages called as the chisel, Scala, which are also used as the verification languages. But these are the industry support for the tools are not that much as compared to UVM or OVM. So first of all, if I categorize it, so the first priority will definitely goes to UVM. So because this is the only methodology which is currently being adopted by every company, every industry. After that, system Verilog will come, and after that Verilog, and after that Python, SB unit. These are also speeding up and trying to compete with the other methodologies like UVM and SB, because these are open source and then easily downloadable. So these are the different careers in which a VLSI industry or the semiconductor industry support. So if a new college graduate or a particular person wants to pursue his career into VLSI, so these are the different subset roles or like subsequent roles which that particular person can anticipate. So the first one is the RTL design engineer. If that person will go into the RTL design engineer role, in which he needs to code that particular RTL design or the using the HTL languages for the particular modules. Similarly, IP SoC design is a subset of RTL design in which the IP design role basically, so one point I list out here in the IP and the SoC. So the IP part needs to be dealing with the complete functionality of the basic building block, but the SoC design engineer never checks the functionality. He only checks the connectivity. He will only check whether the connection between my different IPs and the subsystems are proper. He will never check the functionality whether the particular functionally it is working fine or not. He will do only at the top level, but the clocks and resets are coming. Only at that level he will check the functionality. But apart from that, he is not. So the main functional work or the low level ground work is being done by the IP. Similarly, the RTL integration engineer is also not dealing with any kind of functionality. He is just teaching the RTL design. He needs to since every module has a different set of HTML based code, he needs to stitch that code with the top level, and he needs to mention again the connectivity is ensured. Similarly, for SoC IP subsystem, IP verification engineer is actually doing the groundwork or the functional verification. Subsystem and the SoC verification engineer, specifically the SoC verification engineer is mostly dealing with the connectivity part. So SoC verification engineer, apart from the connectivity, the low power verification, the C model, and all those kinds of things, the SoC verification engineer does. But the IP based verification needs to deal with the functionality of the particular basic building block. Similarly, synthesis engineer, physical design engineer, as I earlier told, the formal verification engineer. This is a new area which has speed up into the last 3 or 4 years. Basically, what happened? When you run a simulation through a test case, it's very lengthy and it takes time. Formal verification engineer or the formal engine, it's a built on an ML-based algorithm which will explore the entire state in a very limited amount of time. So you have a more number of test cases as compared to simulation, because formal is much faster as compared to the simulation. That is the functional verification or the IP verification. But the only disadvantage with formal, it can only be performed with an IP, not with an SoC. If someone performs a formal with an SoC, it can explode and the tool will give up. So these are the different performance implication. Performance implication is also a new area which is like speeding up, like when someone needs to deal with the
verification engineer also perform the case studies.
formal verification engineer.
Also perform case studies.
Case studies.
I mean different sets of data and what are the output.
No, actually the thing is that when you run a simulation, right, in both case of directed and the random, there are some areas which might miss out, because the simulation engine or the simulation technique is being built in such a way it will cover certain amount of state space. If my state space is this one, this entire circle, it will cover bits and pieces into different areas. Whole area might not get covered. That's why formal comes into picture. When I am running a formal verification, it will explore the entire state space using over constraint and under constraint. So that means if I do an over constraint, I need to cover this entire state space that formal verification can cover. But the simulation, normal simulation or my functional verification might not able to cover the entire state space. So that's why formal verification comes into picture. But this is also a disadvantage because I can't perform it into the SOC. As I told, it will go into the entire state space. In SOC, generally there are multiple clocks, multiple gates, and it can't handle those much amount of capacity. So it will explode. That problem is called as a logic code explosion problem. Code explosion problem.
Sir, in your opinion, what are the skill sets that should be possessed by budding engineers so that they can be absorbed into various industries?
Yeah, I'll let you come. So basically, these are the common skills. Common skills means in the kind of when a person is graduating straight out of the college. This skill is not for an experienced professional for more than 4 years. Until 4 years it is valid, but after 4 years the complete skill set changes. So this is basically from 0 to 3 years. So the digital electronics. So if a person goes for any interview, the first thing what they have been asked for is the digital electronics. Without digital electronics, they won't move on to the other sections. So whether the combinational circuit knowledge is good or not. Like for example, there might be some problems related to the multiplexer, demultiplexer, decoder, encoder, priority encoder, adder, loop net, adder, anything that can be. So both the combination sequential circuit knowledge should be fine. FSM means like my Moore state machines, and that too also comes up with the different categories like overlapping state machines, non-overlapping state machine, the sequence detector kind of problem. Similarly, the number system knowledge should also be good. And I'm not talking about only the conversion thing. Like there could be multiple things related to come up with the gray code inverter circuit. They can give that person to explain or kind of a broader circuit. The logic gates thing that thing depends on for example kind of how you can design a full adder with this much number of gates, or how you can design a full adder with half adder, and generally we design a full adder with half adder and 1 more gate. So how you can break that half adder, how you can design a decoder using full adder, how you can implement a counter using mux. So all this kind of techniques will come under anything can ask. And once they found out that person digital electronic fundamental is good, then they will go through the resume or the other things. But before that, they even don't ask anything else. So once this is clear, then that section depends on the company of the advanced digital section whether they will go for it or not. Like the static timing analysis checks, the setup time, hold time, all those concepts they can ask. Related problems like the hold slack calculation, the worst delay calculation of a circuit, all those comes under the advanced digital design part. Once this is fine, then the Verilog VHDL, primarily Verilog. In Verilog, they don't expect that a person could write the entire code, but at least that person's understanding or how he thinks about the problem, that understanding should be there. For example, if I want someone to help me with the deep flip-flop code, whether it's a synchronized reset or an unsynchronized reset. So in that case, that person didn't need to have the complete understanding or syntax-wise correct for the complete code, but how at least the code should behave. Similarly, what are the synthesizable construct, what are the non-synthesizable construct, what I can use in my RTL design code, what I should not use, those kind of knowledge. In the CMOS, basically how the CMOS function, how the MOSFET function, what are the different terminals, how the channel correlation work, what is the latch-up effect, what is electromigration, or how the stick diagrams of the different circuit, metal layer connection. So all those things anything can ask. But basically if someone goes for a front-end design role, the first 3 are mandatory. So if someone going for an RTL design or RTL verification role, the CMOS fundamentals, the Perl, Python, the editor knowledge might not mean that much what is meaning for an RTL design or RTL verification role. If someone going for a like back and roll. Then digital design is everywhere. Digital design is common for both RTL design, RTL verification, or the back and roll. This is mandatory section. After that, only someone will move on to the other section. So the ASIC flow and the GTF flow, that person knows is good. Some of the protocol understanding like AHB, if AHB is not there, it's fine. But at least APB, how APB is varying, what is the state machine of the peripheral bus. Why I am saying this I2C APB? Because these are the common communication protocols. How a module to module interconnection will happen only through these protocols. So these are necessary. So as I mentioned, these are the subdivision. I have not written digital design specifically because digital design is mandatory for all the three. So in verification, they might ask for the OPM and the OPM understanding, the assertion coverage, and AXI 3 and 4 are mandatory. If someone is going for an RTL verification or AHB, those things are mandatory. Custom design part scripting they will ask heavily, and then that will require Python anything of anyone's choice. The analog fundamentals starting from BJT, the common gate configuration, common drain configuration, and in case of BJT it is like the like base emitter collector, all those common configuration. So conceptually they can ask some questions from the analog fundamentals, the in-depth of the CMOS. HTS timing analysis is again very common for the custom design part. They need to understand and completely thoroughly for this part. So this ends the first section. You can take a 5 minutes break and ask.
So what is the scope in VLSI quantum? Sorry, quantum scope in VLSI quantum.
Quantum computing. VLSI quantum.
That I am not sure because it's a new area. It's currently catching up. But yeah, some companies are working on their basically building their decoders out of the quantum computer.
And comparator also are designed using quantum.
Yeah, but it's still very in early stage. So we need to tend to think. But yeah, the other applications like artificial intelligence and other things are slowly catching up with those techniques. Because anyway, I have explained many tools which are currently using the machine learning algorithm, which are previously maybe 5 years back was not there. So the semiconductor industry is coming with utilizing those techniques to like kind of upskilling their tools. But the quantum computing is still very new. It is a scope, it's a very scope, but I'm not sure.
আমি একদম এবি থেকে স্ক্র্যাচ এবি থেকে শিখি।
আমাকে এখানে ওই এগুলো বলে দিতে হবে আপনার এইসব কিসব
হ্যাঁ ওইগুলো আমরা আপনাকে বলা করে দিলাম ঠিক আছে। বড় কথা কলেজ স্টুডেন্টের কথা বলছি। কত জানি না
ডিপ্লোমা করেছি
যারা ওই আর্কিটেকচার যেরকম সিভিল ইঞ্জিনিয়ার হয় না ওইরকম
আমার পরীক্ষা মনে
বেসিক কনসেপ্টটা সিমিলার সব তারপরে তো আলাদা আলাদা ল্যাঙ্গুয়েজে জানা আমার কনসেপ্টটা হচ্ছে কেন ইনফ্লুয়েন্স কন্ডিশন নিয়ে কথা হবে না কিন্তু সিনট্যাক্স গুলো এক্স্যাক্টলি অ্যাকচুয়ালি বেসিক কনসেপ্ট মানে কোডিং মানে অ্যালগরিদম জেনারেট করা ইজি যে কি প্রবলেম আর অ্যালগরিদম হবে লেখার সময় ডিফারেন্ট সফটওয়্যারের ডিফারেন্ট সিস্টেম এইটাকে যেমন ডবল স্পেস এইসব অনেক ব্যাপার ইন্টারন্যাশনাল ম্যাক্সিমাম টাইম মানে ফন্ট লিখবে কটা ইমেলের পর এটা লিখতে হবে ওই ফন্টটা কাজ করবে না হ্যাঁ এই একটা ল্যাঙ্গুয়েজ একটা ল্যাঙ্গুয়েজ বেশি ল্যাঙ্গুয়েজ শিখে ঠিক আছে
পাইথন শিখলে সব
হয়ে যাবে ওই কারণে
হার্ডওয়্যার সফটওয়্যার